Okay, we should be starting now. Okay, so again, let's welcome Jan Vysoky giving his second part of his lecture series on his issues with graded manifolds. So take it away, Jan.
So good afternoon, everyone. Thank you, Mark, for introduction. So hopefully today there will be no more issues, and I will try to tell you something which works. So last time we spent a lot of time, in fact, too much time, trying to understand what doesn't work. So let me find where I finished with something which works. So my last slide last week was definition of graded manifold. So we arrived to the working definition of graded manifold. I will quickly recall what I mean by graded manifold. So I start with the second countable Hausdorff space, such that I have a graded locally ringed space over this topological space. And I say that a pair, open subset, and some map is called graded chart for curly M here. Typo is still here after 1 week. Perfect. If U is an open subset of my topological space, and this phi is an isomorphism in the category of graded local ring space from the restriction of my sheaf of my local ring space to open subset U to a graded domain. And what is graded domain? I defined last time what is graded domain. Graded domain over some open subset is a graded local ring space where this sheaf of functions on this graded local ring space is this sheaf of host sections are this where is this formal power series in some coordinate psi with coefficients in smooth functions on U. Okay, so where am I? Okay, so this is a graded chart, and if I can cover my topological space by graded charts, I call this collection of all these graded charts and graded smooth atlas, and I get something which is called graded manifold. And this graded dimension of my graded domain is called graded dimension of my graded manifold. Okay, so let us find some basic properties of graded manifolds. So first of all, graded manifolds form a category. They form a category which is defined as a subcategory of, as a full subcategory of category of graded local ring space, and a morphism phi from M to N, which is a morphism in the category of graded local ring space, is usually called just graded smooth map or just smooth map. And one can quickly check that if you take your given graded atlas and look, because all these phi's are pairs where one of these maps is one of these elements is a continuous map. So if I take these underlying maps, underlying my charts, and collect them all together, it is easy to check that this A0 is in fact an ordinary smooth atlas on my topological space M, thus making it into an ordinary smooth manifold which has my dimension N0. Recall this, I have this sequence Nj, and there is N0 here, and this N0 is dimension of my underlying manifold M, which I sometimes write as underline of this curly M. Moreover, if you view M, this non-curly M, as a graded manifold, so it's ordinary manifold, but you can view every ordinary manifold as a graded manifold, and there is a canonical graded smooth map going from M to curly M. In fact, if you take a function here on this curly M, on the graded manifold, you define something which is called the body of a function. It's underline F, which is you pull back your function from here to here, and you obtain ordinary smooth function on uncurly M. This is called body of the function. So in particular, if f has a degree non-zero degrees, then body is automatically trivial. If f has degree 0, then it can be non-trivial. But interestingly, there is no canonical map the other way around. So there is no map from curly M to M. So you cannot simply take ordinary smooth function on M and pull it back to curly M. This is not possible canonically. And this is not the case if you are talking about non-negatively graded manifolds. This is not the case. There is a canonical projection, which makes them kind of trivial. And this was my last note last week, is that for non-negatively graded manifolds, in fact, this graded domain sheaf is quite simple because you don't have to work with infinite formal power series, but it is enough to work with polynomials in your size. There is a kind of the most important example of graded manifold, and all the graded manifolds I know are of this form, in fact. So if you start with a graded manifold, then if you take a sheaf, which I denote as gamma E, a sheaf of graded vector spaces, I call it a graded vector bundle, my sheaf. If it's a sheaf of C infinity M modules, meaning that for each open subset U, this is a graded vector space because it's sheaf evaluated on U. This graded vector space has to be a module over this algebra, C infinity MU. This is graded associative algebra, so it must be a module. And the restrictions in my sheaf, gamma E, have to be compatible with the modules. And the second condition, you can say that gamma E is finitely and free, locally finitely and freely generated. And what does it mean? That as a sheaf of C infinity modules, C infinity M modules is locally isomorphic to this sheaf, which assigns to each U just as a product of functions times some graded vector space R and J for some sequence, for some fixed sequence. So for each U, the sequence is the same, and this sequence is called the graded rank of my graded vector bundle. So this literally means that I have some local frames which I can use. And there is this example of prototypical example of graded manifolds. So I take my graded vector bundle over some graded manifold M, and I can define an ordinary vector bundle over M and a graded manifold over this vector bundle. So I define a graded manifold E such that the underlying manifold is this vector bundle, and I have some sheaf of functions on this E, curly E. And there is also a graded smooth map from this curly E to curly M. And so I can take graded vector bundle defined here and produce a graded manifold, which means that I can equip this. I can call this E a total space of my graded vector bundle, and this total space is a graded manifold. And the most usual case how you do it is that you start with an ordinary manifold. So you don't start with the graded manifold, but you start with the ordinary manifold. And as your gamma E, you take space of sections of ordinary vector bundle. So I take ordinary vector bundle over M. I take its sheaf of sections, I shift it by K, and then I obtain a sheaf of graded vector spaces, which satisfies all this stuff. And therefore, there is a unique up to a diffeomorphism graded manifold structure, which is called degree shifted vector bundle. So I can from every ordinary vector bundle, I can construct a graded manifold, which is called degree shifted vector bundle. So this is the most important example of graded manifold. Then there is another question which is quite intriguing, is that how do graded manifolds coincide with supermanifolds or not. Because on the first slide I told you there are two approaches to graded manifolds. So what do my graded manifolds have in common with supermanifolds? And the relation is not so simple. So one direction is kind of clear. So if I start with a supermanifold, which means that what is supermanifold I didn't tell you, but it's again some locally ringed space where this is a sheaf of superalgebras instead of graded commutative algebras. And this sheaf of superalgebras is locally isomorphic to some modal sheaf again, and this time the modal sheaf is just, you take some open subset of Rp, and to each subset of Rp you assign superalgebra, which is tensor product of smooth functions on U times exterior algebra, over Rq. So this is what is supermanifold. And there is a famous Bechel's theorem saying that every supermanifold is in fact super diffeomorphic to a parity reversed vector bundle, which means that I take ordinary vector bundle and this sheaf of superalgebras is in fact exactly the exterior sections of exterior algebra of A star. And there is a obvious Z grading on this algebra. And in fact, what you obtain, so this Z grading makes it into graded manifold. And this graded manifold is in fact exactly this A1, this degree shifted vector bundle by 1. But this construction is highly non-canonical, meaning that this A is not determined canonically. There is no kind of functor you would take a supermanifold to give you some unique vector bundle. It's highly non-canonical procedure, so this is not really canonical correspondence. But the other direction is even more complicated. So it doesn't work always, but if you start with graded manifold, there is always even part submanifold. I will tell you what it is later. But it's some submanifold on every graded manifold. And this submanifold is non-negative. You have to suppose that it is non-negatively graded. And then one can construct up to a super diffeomorphism unique supermanifold S together with a smooth surjective submersion from it's over some ordinary manifold S, and there is some smooth surjective submersion from S to my original underlying manifold. And it's also not a direct functor because you kind of glue together these guys using transition maps of your graded manifold. So it's not unique, it's not functor, it's kind of functor up to the and diffeomorphism. And what is interesting that there is a kind of Bechel's theorem for non-negative graded manifolds. So something similar holds for non-negative graded manifolds, but there is no such thing for these all graded manifolds. To my knowledge, of course, it can exist, but I don't know it. So let me now talk about some usual differential geometrical structures on graded manifolds. So for example, what are vector fields on graded manifolds? So let M be a graded manifold, meaning I have an algebra of functions, graded algebra of functions. So I can define graded vector space whose kth component are derivations of my graded algebra of degree k. And in fact, it is not completely obvious, but this thing defines a sheaf of graded vector spaces. So it's not only an algebra, but it's a sheaf of graded vector spaces. It's not only a graded vector space, but it's a sheaf of graded vector spaces. In fact, it's a sheaf of C-infinite M modules. And sections of this sheaf are called vector fields. So this is how you define vector fields. So this requires some work to prove that it's a sheaf, because you have to define what is the restriction of vector fields. And to define what is the restriction of vector field, it's quite similar to the ordinary manifold case. You have to use partition of unity to define it. So it takes some time, but it works. So I have a canonical sheaf constructed from my graded manifold. And in fact, it's locally finite and freely generated because it's locally isomorphic to C infinity m times R and minus J, where nj is the graded dimension of my graded manifolds. And why there is n minus j here? Because the local generators of this frame are in fact usual kind of coordinate vector fields, which work in the way you expect. And they have, this one have degree 0 and this one have degree minus degree of psi mu. This is why there is minus j here. In particular, this sheaf, it's a sheaf of modules which is locally finitely pre-generated, meaning it's a graded vector bundles in this sense. I told you 3 slides back. And therefore, there is a graded manifold together with a projection, and this graded manifold is called tangent bundle to my graded manifold. And in fact, its underlying manifold is ordinary tangent bundle to my underlying manifold, and the graded dimension of this graded tangent bundle is nj plus n minus j, where j goes over integers. And moreover, there is also a notion of tangent space at M. So what is a tangent space at M? So it's a graded vector space again. This time it's finite dimensional, such that its kth component are degree k derivations of stalk at M, valued in R. And it's a finite dimensional graded vector space. It has graded dimension n minus j. And in fact, there is a canonical surjective graded linear map from algebra of vector fields to tangent space at M. But it's kind of strange here because, for example, it is not true that vector field is determined uniquely by its values at all points. That's not true. There are vector fields which are non-trivial, which have 0 value at each point. So they are equal to 0 vector at each point, but they are not trivial. Okay, so these are vector fields. And what about differential forms? And differential forms are introduced by a cute trick, kind of interesting one. So you start with a graded manifold. And now, because we allow for negatively graded coordinates, also we have to be slightly inventive. So let us choose some even integer such that sum of these degrees, which is possibly negative, plus this even integer is always non-negative. So this is kind of stupid condition on my S, but it doesn't matter which S I choose in principle for all mu's. And then I define a sheaf of differential forms in this way. I take a sheaf of vector fields, I shift it by S plus 1, and this is again a graded vector bundle. So I can construct a corresponding graded manifold, and this corresponding graded manifold is denoted like this. So it's denoted as a degree S plus 1 shifted graded graded tangent bundle, but it's really a graded manifold corresponding to this S plus 1 degree shifted vector bundle. And in fact, because of this degree shift, this S is chosen in the way, then the underlying manifold is still just M, the underlying manifold on my original graded manifold. And I have some algebra of functions on this graded manifold, and I declare it, this is a sheaf, because it's a sheaf of graded commutative algebras, and I declare this sheaf to be a sheaf of differential forms. And why this is, reasonable definition? And in fact, why is that? Because if I start with local coordinates on M, which are x's and x's, x's are coordinates on M, these are these non-commutative, these higher degree coordinates, then on this ts plus 1m, I have coordinates, additional coordinates. I still have these coordinates, but I have also additional coordinates dx, which I denote suggestively as dxi's and dx mu's. And what are their degrees? The degree of this guy is s+1, and degrees of this guy is xi plus s+1. So because this xi's had the degree 0, these have always all the degrees. So these guys anti-commute. And these guys has degrees, this is even, so I don't care about s. So this has degree xi mu plus 1. So if xi's were even, these guys dxi's are odd, and if xi's were odd, dxi's are even. So it is really, these coordinate functions commute as you would expect from differential forms corresponding to these coordinates. And in fact, one can show that on this sheaf, you can kind of write this sheaf as a direct sum of some subsheaves, and there is a well-defined subsheaf of p forms, which are exactly functions here, which are locally sums of monomials in this dx's and dxi's of degree p. So locally, this really look like p forms. And it's a reasonable definition. There is a convenient thing. So for every p form, it's convenient to introduce an alternative grading. So you don't use the grading inherited from this graded manifolds, but you use a slightly different one. So you subtract p times s+1. This looks strange, but it really kind of, you subtract degree s+1 for every d appearing in the local expression for a p form. And this is well behaved grading because now, of course, you would like to have algebra of forms with some reasonable operations on differential forms. So you have a product of forms because it's an algebra of some algebra of functions on some gradient method. So you can multiply forms between them, but there is also analog of exterior derivative, analog of interior product, and analog of Lie derivative, and they are introduced as vector fields on my algebra of functions. Sorry, my kid is trying to break into my room.
Jan, can I ask a question?
Of course.
So this omega that you defined, it's now should be interpreted as the graded analog of the sheaf of forms. But do you still keep the interpretation that the sheaf of forms is also the sheaf of sections of some vector bundle? So
it's not a sheaf of no, it's not a sheaf of sections of a vector bundle. It's a sheaf of functions on some graded manifold.
Yeah, I understand. But in classical differential geometry, you can take
the
direct sum of all the exterior powers of the cotangent bundle, and the sections of that, they coincide with the sheaf of.
And in fact, and that's true. You can still, I think, it's true that in fact this sheaf of differential forms, it defines a sheaf of. It still defines a sheaf of infinite m modules over my graded manifolds.
Okay, and they're well enough behaved so that you can interpret them as locally free, and so defining.
They are still. Okay. I think it's still not all of these forms together, but p forms are always finitely and freely generated sheaf of infinite m modules over my graded manifold m. That's true.
Okay, thanks.
Okay, so but what is now funny that my differential forms, they are functions on the graded manifold, so I can introduce all the operations, all the derivations of my algebra of function of my algebra of differential forms as a vector fields. And indeed, they are introduced as vector fields, and there is notion of exterior derivative, which makes a p form into p+1 form, and it preserves this newly defined degree. So this bracketed degree here means this one, this degree, and it preserves this degree. Interior product shifts this degree by the degree of a vector field I plug into it, and Lie derivative also shifts this degree by the degree of a vector field I use for my Lie derivative. And one obtains a full set of Cartan relations. And observe that there is no S here in the degrees of my exterior derivative, interior product, and Lie derivative. And there is also no S, this even integer, appearing in any of Cartan relations because it's even. So in any sign rules, there is no S appearing. You can always make it go away. So this S is important only for the construction on the graded manifold, but not for forms themselves. It's not really important. And if you have exterior derivative, of course, you can define the theorem cohomology of your graded manifold. And because it preserves this degree deck, you can define it degree-wise. So for each k, you can define separate the theorem cohomology of degree k. And but it's in the end, it's quite boring because for non-zero k, it's trivial. And why is that? Because for any closed omega of degree k, you can define there is some there is a, because there is a special vector field on every graded manifold which is called Euler vector field, which simply multiplies function by its degree. And therefore, you can write any omega as 1 over k. No, that's not true. But I should say what there is a typo here, and there should be some omega prime here, and I'm claiming that omega is d omega prime. You can define the potential for my closed form by this formula. So I take omega prime to be 1 over k. I plug my Euler vector field into omega. I obtain some p minus 1 form such that d of it is omega. So I can easily show that every closed form of degree different from 0, because I have to divide by k here, is actually exact. So it's trivial, and one can show also that so this is not true for degree 0 forms, but for degree 0 forms I can show using some arguments, using double complexes, blah blah blah, that that every cohomology of degree 0 is in fact isomorphic to ordinary theorem cohomology of my underlying manifold. So all the non-triviality is in fact hidden in my manifold M. And also it's true that Poincare lemma still works. So every closed degree 0 form is locally exact. So this is still true. Okay, so another differential geometric baby we would like to have is a inverse function theorem. It works very nicely. So for every graded smooth map, there is always an induced map of corresponding tangent spaces at the corresponding points. So for every point, I can define a graded linear map from here to here, and it has usual very nice functional properties. So tangent map to identity is the identity. Tangent map to composition of two maps is a composition of two tangent maps. Therefore, I can define the rank of my graded smooth map at some point to be a rank of this graded linear map. It's a graded rank because it's a graded linear map. So it's a collection of these linear maps, and each of them has a rank. And altogether, this gives me some sequence of non-negative integers, which is called graded rank of my map at phi. And if I have tangent map, I can say what is local graded diffeomorphism. So some graded smooth map is a local graded diffeomorphism at some point if tangent map is isomorphism in the category of graded vector spaces. And in particular, and this is quite important, local graded diffeomorphism between two graded manifolds can exist only if they have the same graded dimension. It's obvious because the graded rank of tangent space is almost the same as graded dimension of M, except it's kind of labeled backwards, but it doesn't matter. So I necessarily there can exist local graded diffeomorphisms only if my two graded manifolds have the same graded dimension. And this is one of the questions Vitek asked last time. So in fact, every graded diffeomorphism is a local graded diffeomorphism, which kind of follows from this composition rules here, trivially. And therefore, two diffeomorphic graded manifolds must have the same graded dimensions. So for example, if there are two graded domains of the different graded dimensions, they cannot be graded diffeomorphic. So this graded dimension is really invariant in my category, kind of. And there is this IFT. So if I have a local graded diffeomorphism between two graded manifolds at some point, there is an open subset, open neighborhood of my point, such that the underlying map of phi restricts to a diffeomorphism onto its image, and my phi restricted to U defines a graded diffeomorphism from M restricted to U to N restricted to its image of U under this underlying smooth map. In fact, what is interesting that, in fact, in usual differential geometry, you have that local diffeomorphism is a diffeomorphism if and only if it's bijective. And here, there is slightly stronger statement that phi is a graded diffeomorphism if and only if it's a local diffeomorphism at every point, and it is enough that the underlying map, the underlying smooth map, is a bijection. So in fact, graded diffeomorphisms are not very complicated beasts, because kind of on the level of underlying map, it's the same as ordinary differential geometry, but in these higher degrees, it's decided entirely in the first degree derivations of my maps in coordinates, basically. If I have inverse function theorem, I have kind of reasonable notion of immersions and submersions, for example. So I say that phi graded smooth map is an immersion at point if this tangent map is injective, and it's a submersion at point M if it's surjective. So very kind of usual notion of immersion and submersion. It implies that the underlying map of my graded smooth map is an immersion and submersion, respectively. And what is important that I can use inverse function theorem to provide the usual convenient graded charts around the point where you have immersion. So it's completely analogous to ordinary geometry. So if you have immersion, you have some very well-behaved coordinates such that locally your map looks like, you know, you include some plane into vector space, and submersion locally looks like just like a projection onto some coordinates. So this works in the same way here. And if I have immersions and submersions, I can talk about submanifolds. So what are submanifolds? So it's my time. Okay, nice. So I can now talk about submanifolds. So if I have a graded manifold M, I can declare a pair of a graded manifold and some graded smooth map, and immerse submanifold if this J from N, I should say that this J is mapped from N to M. And if this J is an injective immersion, which means that it's immersion at every point and the underlying map is injective, then I call this pair an injective immersed submanifold of my graded manifold M. I call it an embedded submanifold if moreover, if it's an immersed submanifold and moreover, the underlying map from N to M is an embedding. So usual notion of an embedding, and it's closed embedded submanifold of M if image of this underlying smooth map is a closed subset of M. And there hold usual properties of submanifolds. So for example, something which I call extension lemma. So if I have an embedded submanifold, there is an open subset in M which contains the image of N, such that the pullback by my embedding map evaluated at Y, because it's a sheaf morphism, so I have to evaluate it on some open subset, and then I obtain a graded algebra morphism from functions on M on an open subset Y to global functions on N, and this is a graded algebra epimorphism, which means basically that any function here on your embedded submanifold, global one, can be extended to some smooth function on the ambient manifold. If it's just embedded, you cannot extend it to the whole M, but just to some open subset of your image of N. And you can show that it is closed embedded submanifold if and only if we can choose, in fact, this Y, this open subset Y, to be entire M. So for closed embedded submanifolds, you can extend all functions on your submanifold to the function on the ambient manifold. So it's very useful property of embedded submanifold, and this is the reason why they are important. And it's interesting that there is also some very nice algebraic viewpoint on submanifolds, which is the same as in algebraic geometry. So it's not that interesting, but to any submanifold, in fact, you can associate a sheaf of ideals in your sheaf of smooth functions, and it's defined for each U to just as a kernel of my embedding map. So it's a kernel of pullback. So it's basically consists of function which vanish if I pull back it to my submanifold. And this is in fact a sheaf of ideals, meaning it's not only ideal for each U, but it's a sheaf of ideal, meaning that restrictions are compatible with this with this ideal. And also, if you glue local sections of which all lie in this ideal, then the glued section will also lie in the ideal. So it's really something which is called sheaf of ideals. And this extensional lemma in fact shows that if N is closed and J is closed embedded submanifold, then you can basically view this sheaf of functions on your closed embedded submanifold as a quotient of the ambient sheaf by this ideal. There has to be pushed forward because they are not sheaves on the same topological space, but it is not really important. So you can really calculate all the algebras here using this ideal and this ideal. And in fact, what is interesting that there is a class of ideals, global ideals, just ideals, not sheaf of ideals, but ideals in this algebra, which uniquely correspond to closed embedded submanifold, and they are called regular ideals. And you can show that to every regular ideal there is unique closed embedded submanifold up to the theoremorphism, and you can show that this sheaf of ideals is in fact a regular ideal. So there's a nice algebraic description, and let me give you some nice examples. Not nice, they're kind of stupid, but some interesting examples of submanifolds. So recall that we have a graded smooth map from the underlying manifold to the graded manifold itself. And one can easily show, it's very trivial in some coordinates, that in fact this makes this pair M and IM into a closed embedded submanifold of my graded manifold. So I can view the underlying manifold as a closed embedded submanifold of my graded manifold. And there is cute consequence of this observation, saying that the body map is surjective. It's because of the extension lemma. It now says that I can take any function on M and extend it globally to a global function on curly M, such that pullback of this function here is my given function, which basically means that the body map is surjective. And the corresponding sheaf of ideals is, of course, therefore just functions such that their body is trivial. So this is my ideal, sheaf of ideals corresponding to my submanifold. There is another example saying that points are submanifold. What does it mean? I take a sheaf of ideals defined like this. So for every, so I fix a point M, and for every open subset which contains M, I declare this to be functions which such that their body vanishes at M. And this defines an ideal. And if U doesn't contain M, I declare it to be all functions on U. And this is a sheaf of ideals, and it's a regular ideal. Therefore, it corresponds to some closed embedded submanifold. And in fact, the corresponding closed embedded submanifold is a singleton submanifold. So it's a submanifold which consists, the underlying manifold consists of just the point M. And my sheaf of functions on my submanifold, there is only one open subset, the entire N, right? And this algebra is equal to R, viewed as a graded associative algebra, and which corresponds to kind of functions on single point manifold. So it's just reals. And it's denoted like this. So I can view points of my underlying manifold as a submanifold, trivial submanifold. And there is even submanifold. It's an interesting one. I told you about this in this slide of relation to supermanifold. So I consider the following sheaf of ideals. So I say that functions is a section of my ideal over U if all the local representatives of my function, which basically local representatives, I didn't tell you what are local representatives, but I simply restrict my F to some chart and map it using chart to a graded domain. And here in graded domain, this local representative is a section of a graded domain over this open subset. And it has to live in the ideal generated by odd coordinates. So I take all the odd coordinates, so I use all the odd ones, not the even ones, and I generate ideal in this algebra. And if local representative lives in this ideal, for all alphas, I declare this to be an ideal. And I can again show that this is a sheaf of ideals and it satisfies all the good properties. And then this M0, which I define, now I can define it literally as a quotient of my C infinity M over this ideal. This is a sheaf. And you can show that this is a closed embedded, this makes it into an embedded manifold. And in fact, this is a closed embedded submanifold of your manifold. And there are some interesting challenges in the process. So if you'd like, for example, to define a level set or intersection of submanifolds, so how would you do it? So there is a manual how to do it. So first, how to define an inverse image of a submanifold. So what I mean by it, so I start with some embedded submanifold of M, and I start with a graded smooth map from S, some graded manifold S to M. And because N is a submanifold of M, I would like to have something like inverse image of my graded submanifold N here in S. So some submanifold in S, which will be an inverse image of my N using phi. And of course, you cannot define it straightforwardly because this curly S, curly M, curly N, they are not sets, right? So it's not that easy. So how to define it? So I would like to have some embedded submanifold, which I denote as inverse image of N. And the correct definition, which I think is correct, is to define it to be a pullback in the category of graded manifolds. So what is a pullback? It's a diagram of this form. So I have phi here, j here, and I have to construct new maps I and phi hat here. They have to be graded smooth maps, and this I has to be an embedding. And there is also a universal property which is very important. saying that if there is another such diagram, there is a unique map from this guy to this guy, right? So, and it is a good definition. And there is also interesting observation that if n is compact, so this underlying manifold of n is compact, and this J is closed embedding, in fact, so this is a closed embedded submanifold such that n is compact, and one can show that, in fact, the ideal corresponding to this submanifold here, it's push forward because they are on different spaces again. But if you push forward, it's in fact exactly the pullback of this ideal corresponding to n. But only for compact n, I believe, because I think it doesn't work for non-compact n. I'm not sure, but I think so. But definitely for compact, it works. And there is example where this inverse image submanifold exists and it forms a categorical pullback. Therefore, it's unique up to a diffeomorphism. And this is the case where this map phi is transversal to my manifold. So it's very similar sufficient conditions as for ordinary manifolds, where if you start with a map which is transversal to your submanifold, you can take its inverse image and its submanifold again. And what the transversality is described here. So I, at every pair of points such that they map to a given point M, the tangent space to M at M has to decompose as a sum of images of tangent spaces. There is no direct sum here. And then this phi minus n can be constructed and is unique up to diffeomorphism by the universal property. And it can be constructed, but the construction is quite involved. I have no simple construction, but you can construct it. So you can do inverse images of some manifold, which is cute. And this allows you to define everything you need, basically. So some examples. So for example, level set of what is a level set of a map between two graded manifolds. So you have to assume that M is a regular value of your map, which means that at all points from the inverse image to M, phi is a submersion at all those points. It's the same definitions and is an ordinary case. Then in fact, one can show that phi is transversal to this singleton submanifold corresponding to point M. Therefore, its inverse image exists, it's unique up to diffeomorphism, and you can call it a level set corresponding to your M. And in this case, the underlying set here is just a single point, which is compact, so you can use this formula and you immediately know exactly how does the ideal, the kernel of your embedding looks like. It's just a pullback of these functions vanishing at point. There's another example, also very useful, how to define fiber product of two submanifolds, of two manifolds. So you take two maps, phi and psi, from S to M, N to M, and there is canonical diagonal map from M to M times M, which makes, similarly to the usual case, M delta into closed embedded submanifold. So you can view M as a closed embedded submanifold of M times M using this diagonal map. So this is closed embedding, and therefore you can calculate the inverse image of this using the map phi times psi, and this is closed embedded submanifold if it exists. If it exists, it's closed embedded submanifold called the fiber product over M. And it has all the good properties of fiber product, and the sufficient condition is that if this phi and psi are transversal, then it exists. So for example, if they are surjective submersion, it exists. I think it's enough that one of them is surjective submersion and they exist, for example. So it's completely the same to ordinary case, which is nice. And then you can also define intersection of submanifolds. So if you take two inverse submanifolds, you say that they intersect cleanly if there exists a fiber product over these two J's and J prime. And then you call this fiber product intersection, and you can construct, this is in fact this connecting map phi hat here it's the immersion of this guy into M then. So you can construct intersections of some manifolds. So this is to show you that some differential geometric constructions work as expected, but it requires quite a bit of work, but it works. And there's another example which is something which I call graded Lie groups and graded Lie algebras. So your category of graded manifolds has some nice categorical properties. First of all, it has binary products. It's a very important thing. So if I take two graded manifolds, I can make their Cartesian product together with some projections from the product to n. In fact, this graded manifold, the underlying manifold is of course the Cartesian product of m and n, underlying manifolds of m and n. Underlying maps of this pi1, pi2 are just projections, so it's not very complicated. And it has, what is important, it is really a product in the category, meaning that it has the universal property such that to any pair of maps from some third graded manifold to m to n, there exists a unique graded smooth map which goes to the Cartesian product such that composed with projection, it works as expected. So this is called universal property of binary product, and it is valid here. So you can construct graded manifold with this property, therefore it's unique up to graded diffeomorphism, blah, blah, blah. And second, the category of graded manifolds has a terminal object, which is this singleton graded manifold I told you before. So it's a graded manifold over a single point where this sheaf assigns to this open subset graded algebra R. To M, there's another open subset which is empty subset, and it has to be trivial on the empty trivial algebra of empty set. Therefore, the following definition makes sense. So I can define graded Lie group now easily just to be a group object in my category. And what is a group object? It's a four tuple of objects. So G is an object in my category. So G is a graded manifold. And there is a multiplication map, group multiplication map, which is a graded smooth map because we are in category of graded manifolds, which goes from the product of G times G to G. And this is why I need binary products. Then there is a graded smooth map, which goes from G to G, which is called graded group inverse. And there is a group unit, which can be viewed as a graded smooth map from terminal object of my category to G. This is important. I need terminal object to do this. And there is a bunch of commutative diagrams between these three maps, which kind of resembles the group axiom. There is no space for them here. And therefore, I can define what is a graded Lie group. There is some simple remark one can show easily, that's completely trivial, that graded Lie group is a graded manifold, so it lives above some underlying manifold. And if I look at the operations, which are graded smooth maps, I can look on the underlying maps of them, and this four tuple becomes an ordinary Lie group. So, so every graded Lie group lives over an ordinary Lie group. I'm sorry. And there is simple example that every graded vector space can be viewed as a graded Lie group. And why is that? Every finite dimensional vector space, to be precise. So I can take every this F stands for finite dimensional graded vector. F means finite dimensional, real graded vector space. And it can be viewed as a graded vector bundle over a point. And there is a corresponding graded manifold corresponding to it using this kind of general construction. So, but it's quite easy. You just choose some graded basis, and you can directly define this graded manifold structure here. And in fact, this assignment, which to every finite dimensional graded vector space assigns a graded manifold, is a functor. It's a functor from category of G finite dimensional graded vector spaces to the category of graded manifolds, and this functor preserves binary products and terminal objects. So I can now take graded vector space, and there is canonical 3-tuple of operation which makes this 4-tuple into group object in this category of graded vector spaces. They are completely trivial. This mu prime is induced by addition, this I prime is induced by subtraction, and this E prime corresponds to a 0 vector in my graded vector space in a sense. And therefore, if I have a group object and I have a functor which preserves products and terminal objects, I can apply functor to everything, to all the objects and to all the maps, and I obtain a group object in category of graded manifolds, and this makes this 4-tuple into gradedly group. So every graded vector space can be viewed as a gradedly group. And there is also a natural notion of morphism of gradedly groups. So we have a subcategory of gradedly groups, and there is one observation that, of course, G is an underlying manifold of this capital G, caliber G, and this inclusion, because this is a gradedly group, this is a Lie group, therefore a gradedly group, this is gradedly group, so this map is a morphism of gradedly groups, just simple remark. And then, of course, if you have gradedly group, you can talk about gradedly algebras. So what is gradedly algebra? So it's graded vector space together with a linear map from G tensor G to G. One, of course, uses this binary notation, which is more common, so bracket notation. So bracket of x and y is this multiplication evaluated of x tensor y. And you assume that this bracket is graded anti-commutative, which is written here, and it satisfies the graded Jacobi identity. Graded Jacobi identity. And there is a notion of morphism of gradedly algebras. Therefore, you obtain a category of gradedly algebras, of course. And there are two simple examples. So if I take a graded vector space, and I told you we have this internal home on the category of vector spaces. So I take internal home from V to V, which is this graded vector space, degree K maps from V to V, linear maps from V to V. And this forms a graded vector space, and I define a bracket. So if I take two maps here, I simply calculate the graded commutator of two guys, and this makes this space into graded Lie algebra. So similar to the ordinary case, for every vector space, you have a Lie algebra of general linear maps. Here's the same thing. And another example, of course, the very important one, if you take a graded manifold and you look at the graded vector space of vector fields over U, it forms a graded Lie algebra under the ordinary graded commutator of vector fields. So it's another example of graded Lie algebra. And now, just the last slide, in fact. So then you have to think a bit how to define left invariant vector fields. So I start with a Lie group, and I want to have left invariant vector fields, and this is not completely obvious how to do it, but you can do it. So you can look at G times G, and then there is, if you take a vector field here, you define vector field 1 times x, which means it's a vector field which kind of locally contains only, it's just x, but using the coordinates only from the second copy of G, and it doesn't contain any derivations in directions of the first copy of G. So it's kind of natural vector field you can construct, and this vector field here has to be, it's a vector field on G times G. This is vector field on G, and you simply want them to be mu related, which means that this is well defined for graded manifolds, because it simply means that this vector field applied on the pullback of function from G is the same thing as a pullback of this vector field acting on the function. So it's very natural condition, and this is good notion of left invariance, and it coincides with ordinary notion of left invariant vector fields in ordinary differential geometry. Left invariant vector fields form a subspace of all the vector fields, and denoted like this. And one can show that it forms a graded Lie subalgebra. It's trivial because the mu relation is preserved by commutators. It's easy to see, and therefore it forms a Lie subalgebra. And in fact, the tangent space to G at the unit of the underlying Lie group G. So this is a tangent space to my graded manifolds at the unit to my underlying Lie algebra. It's canonically isomorphic to the algebra of left invariant vector fields. So there is a isomorphism which to each vector here assigns a vector field. One can show that it's an isomorphism, and therefore it's completely the same as ordinary differential geometry. You can take any graded Lie algebra, graded Lie group, take tangent space at this unit of the underlying space, and define a Lie bracket there, graded Lie bracket there. And because it comes from graded commutator of vector fields, it's trivially graded Lie algebra. So you obtain some functor from graded Lie groups to graded Lie algebras. You have to think a bit that it's a functor, so it takes a morphism of graded Lie groups to graded morphism of graded Lie algebras, but it's true. So every Lie group, graded Lie groups, has its associated Lie algebra. And what is, I think, not very pleasant here, that the converse is most likely not true, because first of all, the notion of exponential map is a bit problematic. I don't know a good notion of exponential map yet. And also there is one note here. I told you that vector field is not determined by its values. So it's a kind of phenomena appearing for graded manifolds. And for example, here, if you evaluate this vector field at the unit, you forget almost everything about your vector field. So I doubt that the converse will be true, that I can integrate Lie algebras to graded Lie groups all the time.
Sorry, is this the fact that you mentioned before, that the vector fields are not determined at one point?
By their values at points. No, yes, I mentioned that at the beginning here. Because in usual geometry, vector field is uniquely determined by its values at all the points. So if you collect all the values at every point, it determines your vector field uniquely. And it's not true for graded manifolds. So for example, this Euler vector field here, where it is, here this Euler vector field, values of this Euler vector field at all the points are zeros. So its value at every point is zero vector in your tangent space, but the vector field itself is not trivial. So you kind of forget about a lot of stuff if you evaluate vector field at the point. Okay, so submanifolds and graded Lie groups. Yeah, there were two examples of things which work very similarly to the ordinary case if you are a bit clever. Not too much clever, because I was able to come up with the notions. So some summaries. So for graded manifolds at the present moment, things that work with no big issues are graded symplectic geometry. So you can define graded symplectic structure with no big problems. You can say what are not just differential forms, but you can define what are multi-vector fields on your graded manifold. There is a canonical bracket of your graded vector fields, which is Coulter-9 bracket. Therefore, there is also a good notion of graded Poisson geometry. So you can define what is graded Poisson manifold on your graded manifold. But there are some things that they are work in progress. For example, it's not clear how to define flows of vector fields, which is unfortunate. For vector fields of non-zero degree, it's kind of easy, but for vector fields of 0 degree, I don't know how to do it yet. This is one of the reasons why I don't know how to define exponential from Lie algebra to Lie group, because of course exponentials, they are basically just flows of left invariant vector fields or right invariant vector fields. So I don't know how to do it yet. What should be easy is notion of a distribution and graded Frobenius theorem, but I didn't have time to check that everything works. And also, if I told you that graded symplectic geometry works, they should be analog of graded Darboux, which again suggests to use some version of Morse lemma, and this Morse lemma suggests again that we have to figure out somehow what is a flow of a vector field. And also integration of graded algebras should be somehow examined a bit further. But yeah, so that's basically all what I wanted to say. So I hope I attracted you to graded manifolds a bit. I'm planning to publish a kind of paper containing all these technical statements. So somewhat introductory paper to graded manifolds, which will contain everything. But it's getting huger and huger, and I planned it to publish it during autumn, but of course I won't be able to do it, so I will probably publish it in winter, hopefully. So stay tuned, and I would like to thank you for your attention.
Okay, so thanks, Jan. And if you guys want to unmute yourselves, feel free to give him a clap and say thank you. So. And if you have any questions, just unmute yourself and ask. I might start. How do Jan? How do principal G bundles work in this picture?
No idea.
No idea.
But I think it's not. I think it's not complicated enough too much, because there is a notion of Lie group actions, right? So this is first thing. I have a notion of Lie group action.
Mm-hmm.
I think I should invent some notion of general fibered bundle. This is also not done yet, but I think it should be quite straightforward, because there is a notion of diffeomorphism, so probably something which is locally diffeomorphic to product should work as expected. So I guess fibered bundles would be fine. The groups should be fine. Actions of graded Lie groups are fine. There is a notion of fundamental vector fields or infinitesimal generators of graded Lie group actions. So it should be straightforward. Okay. I hope. It should be. Of course, they can arise some nasty stuff, nasty things, but it should not. I think it should be okay. I am planning to include it in the paper somehow. I will maybe first write some basic paper which will contain the definitions of graded manifold itself, and then I will add more stuff as a consequent papers, like graded manifolds 2, graded manifolds 3, and yeah, who knows? I don't know. But it should be fine.
Questions?
Okay, may I have a question?
No.
So
yeah, sure,
do I have? First of all, thanks for nice talk. And I would have a bit intrigued question on slide 26, where in general there are traditionally two approaches how to define vector fields. Mm-hmm. And surprisingly, on the level of category of smooth manifolds, and for me, surprisingly, as well for category of supermanifolds, we have canonical isomorphism between vector fields defined as sections of vector bundles and modules of derivatives of smooth functions arising on your manifold. Is there any connection of these two quantities in your setup, or do you think?
Sure. I'm not sure. I still don't know if I can interpret if I can interpret, for example, here in this, where it is here, I start with a sheaf of graded vector spaces, which are called graded vector bundle if it's locally finitely freely generated and it's a sheaf of simple M modules. And then I construct from it, I construct a graded manifold. And of course, I would like to somehow recover my original sheaf, gamma E, from my E itself. And I'm not completely sure if that is possible. And this will answer your question, because if it is possible, of course, I can take my sheaf of vector fields here, which is just a sheaf of graded vector spaces, which is a sheaf of infinite modules, then construct graded vector bundle, and then recover vector fields again as a sheaf of sections of this graded vector bundle. But I don't know. I don't know yet if there is a good notion of section of graded vector bundle. If I start with this kind of map, I don't know. I'm not sure how to recover them yet. I don't know. But it's a good question, and definitely this, and this is very similar to actually Mark's question. I should elaborate a bit on the theory of fibered spaces over graded manifolds, so fiber bundles over graded manifolds. And if its theory is any reasonable, there should be sections of fiber bundles, and there should be vector bundles, there should be sections of vector bundles which are modules, etc. But I am not sure yet. I have no.
Yeah, and do you claim you have any formulation of Bachelor theorem for ungraded setup?
Yes, for non-negatively graded, there is a Bachelor theorem, and this Bachelor theorem basically says that where is my example? This D example case. So look at this D example, and basically this Bachelor theorem for ungraded says that every graded manifold can be constructed from a graded vector bundle over an ordinary manifold. So I start with a graded vector bundle here, but I start with a graded bundle over ordinary manifold. So I don't start with a graded manifold. I start with an ordinary manifold M, which is of course a graded manifold, and I take a graded. I consider a graded vector bundle over an ordinary manifold, and I construct a graded manifold out of it. And this graded Bachelor theorem says every non-negatively graded manifold is of this form, non-canonically, of course. This graded vector bundle is not uniquely determined. It's, it is arbitrary, basically. Not arbitrary, but it's not uniquely determined in any sense. There is a paper on it. I think it's called, I don't know where it is. They sometimes call it they usually call it not just Bachelor theorem, but they call it Serre-Swan theorem, because it uses Serre-Swan theorem, saying that every projective finitely generated blah blah module over functions is in fact a vector bundle or something. I am not sure about the adjectives, so I don't know it's projective finitely blah blah. I'm not sure, but it's called Serre-Swan theorem, and they call it just Serre-Swan theorem for graded manifolds.
So I have a question. Jan, so you mentioned already a couple of times that evaluating a graded vector field at a point loses some information. So you don't have all the information about the vector field given all the evaluations.
Yes.
But if I'm not confused, then if you replace evaluation by a point, which is just an ordinary point, if you evaluate at graded points, like a graded manifold where the base is a point, the body is a point, but then it has graded directions. Then like super points in super geometry.
Yeah, that should.
Then you should be able to recover all the information from all these possible evaluations.
Yeah, there should be some notion of a functor of points.
Right.
Here also, and there is definitely.
Okay. Do you think that?
But I don't understand it yet.
Okay, but
I was not talking about it.
If you were to find the right notion, do you think that you could use it to enrich the Lie functor, which associates Lie algebras to these graded Lie algebras to graded Lie groups, where you replace evaluation at a identity point by some, like thickened identity point?
That would be cool. That should be that would be interesting. And of course, I was also thinking about replacing, for example, instead of tangent space as a sheaf of as a graded vector space of derivations of stalk at point. For example, if you will look at the stalk of sheaf of vector fields instead at the point, it has more complicated structure, more resembling. No, it's not a tangent space. That's not, because it has to remember some neighborhoods. Okay, but I don't know. But the functor of points is, of course, something I have to understand somehow. This notion of, this generalized notion of points in my category.
But in the better studied world of supermanifolds and super Lie groups and super Lie algebras, is something like that already done? Looking at left invariant vector fields at a super point at the identity?
No, I don't know.
Okay.
I'm not aware of it. But
there's something obviously wrong with it, with the idea, which I don't see at the moment.
But I have to say I don't know. Yeah.
Okay.
But I think in the book, because I use mostly the book on supermanifolds, which is called Mathematical Aspects of Supersymmetry, or Mathematical Foundations of Supersymmetry, I think it's called. It's by some Italian people, by
Daure and Frey?
Italian people, Rita Fioresi, no. Yes, I think so. Rita Fioresi, somebody.
Okay,
3 people. They wrote a nice book called Mathematical Foundations of Supersymmetry, which looks. This is exactly they use exactly the same language I used here for supermanifolds. So they are local ring spaces, blah blah blah, and they define Lie groups and Lie algebras in the same way as I did. So they have maybe some reasons to do that. And there is also a notion of functor of points. So they didn't, at least they didn't consider it. But I cannot say that it can be done. It can't be done. I don't know.
Jan, can I ask another question? Suppose you have some fixed Lie group. How rich is the structure of graded Lie groups, like with this as their underlying Lie group?
I don't know.
Like, so I think that if you have like an underlying Lie group, you can have multiple, like there are probably many different types of graded Lie groups that have this as its underlying group, but that maybe there's some constraint, right?
That's an interesting question, which I am always supposed to answer. It's a very interesting question, of course. But the problem is with the graded Lie groups that I don't have any relevant examples.
Right. Okay.
So I just defined them as the most reasonable way I was able to, as a group object in my category, which is, I think, the good notion, right? Because what else would it be? But I have I don't have any reasonable examples like group of orthogonal graded maps or something. I have to think about this and find some nice example, and then it would be more clear.
Yeah. Yeah.
Like, for example, if you would have some group of graded invertible maps or something, and
yeah, I guess I'm just interested in like whether or not you can have like interesting group structures that are kind of non-isomorphic at the level of graded Lie groups, but have the same Lie group as their base. Kind of.
yes, I don't know, but
okay, yeah, cool. Thanks.
It's an interesting idea to try to, and of course, I would answer this question after I will find some relevant examples of graded groups, of course, because so far I only have stupid examples as are shifted by 3 or something.
Yeah, sure.
Yeah, then I can actually answer your question, because you can take graded groups which are just shifted vector spaces, and if you shift them by different numbers, they are not diffeomorphic because they have different graded dimension, and the underlying Lie group is trivial for both of them. Because if you just shift R by non-zero integer, then the underlying Lie group is a trivial one.
Right.
So I have 2 non-diffeomorphic Lie groups which are over the same trivial Lie group. But it's a stupid example, but it's an example.
Right, but the base Lie group isn't really like it. I mean, I don't know. You take your favorite Lie group, and I was kind of wondering whether that imposes, like the group structure on this Lie group imposes constraints on the structure of the graded Lie group. And if you have a point, then there's like not really any group structure, right?
Of course, yeah.
But,
it's an interesting question, and of course it would be nice to construct more explicit examples of
sure. Ones which aren't just kind of take a group and then kind of do something boring over it.
Yeah, sure.
Yeah. Okay, so are there any more questions? No. Okay, if there are no more questions, we might officially close it, and I'll stop recording.